Hello all. So let's discuss now the deep generative models and we will see what deep generative models are. This is under generative AI which can generate images, text or any form of data or maybe translate from text to image or from text to text like chat GPT and stuff. So let's continue and we'll also continue with the Python hands-on in subsequent videos. So let's motivate ourselves that why or what a generative model is capable of. So if you can see this figure on the right side, then if I'll ask whether this image is real or fake, what can be your answer? The correct answer is this person doesn't exist. This is an AI generated image and you can see the clarity of expressions and neatness. No one can say that this is fake, right? So this is what a generative model is capable of. And same if you have used the chat GPT, which is really a hype around. So in that case as well, you can see like it can answer almost all the questions that you ask, right? Although there are some flaws, but yeah, almost everything that came into your mind can be answered, right? So what is it? So we have already seen before that in supervised learning we know that we have x, that is our input data, and the label along with it. So for example, let's consider a very lame cat dog classification problem. So here we already have images in our folders and we already know that it is in the cat folder and there are some images in the dog folder. So we already know and our model knows that which is the cat image and which is a dog image. So we already know the labels or the classes. So in that scenario, the goal is to learn the mapping from this X to Y. So we use some CNN or some machine learning model or whatever to just classify these images. So classification, regression, in regression we find some value. So for example, stock market prediction or some a number that we get at the end. That's a regression problem, right? So at the end in supervised learning, we already know what is the label, but in generative model we use unsupervised learning regime. So where we don't have the labels. So here we just have the data, that is our data set. So for example, if we have to generate the images of people that we have seen in the previous slide, then you just have the images of those people and there is no labels. And model will try to learn those distribution. So at the end, it is a distribution. Okay, it will be clear in subsequent slides how it is a distribution. So at the end the goal is to learn that distribution of underlying distribution of the given data set, right? And for example, clustering. So a good example can be a prime customer. So let's say these are prime customers in our space and let's say this is our non-prime customers. So you can clearly cluster them in a given space, right, in a 2D 3D or 4D if that matters. So that is clustering. So here we are not having any labels that these are prime, these are not prime, but we are classifying them. Like we are putting in the groups, not classification, but we are putting in the clusters of groups that this people are prime, they will be given special service as compared to others. So this is one of the real life scenario of this unsupervised learning or clustering to be precise. And the same goes for PCA, which we already have seen in our one of our videos, right? I'll put the link in the description if you want to. So dimensionality reduction, we already know we reduce from 100 dimension to 2 dimension. So whatever in 100 dimension data represents, same information a 2D data will represent. Of course there will be some loss, but almost 90 to 95% of information will be there. That is what PCA is. So I won't go into that detail right now. So let's continue that how a deep generative model works now. So having motivated ourselves, so as I said, let's say this is our data of faces, right? So and let's say this is a distribution of them. So you can see like what is distribution here, like all those, and we denote it by PD of x. Let's say data distribution. The D subscript is for data distribution. And the goal is with some DGM, which is our deep generative model, we have to learn that P theta of x, which is our model distribution now. So our model distribution we try to learn from our data distribution using some deep generative modeling, and our end goal will be that this two should be same. So the goal should be take input training samples and generate new samples. Those are similar to the given training samples. And in unsupervised learning, in fact, there is an fundamental problem of density estimation. This we also call density or probability distribution or probability density. So there are different terms. But so in unsupervised learning, it is one of the fundamental problem, and this is being addressed by deep generative model. So again, I'll repeat that the end goal is to learn this distribution, right? But how can we learn this distribution? So there are many flavors, but here we will focus on two distinct flavors which are really important and which are used in our real life scenarios. That explicit density estimation, that is, we will find explicitly our model distribution, whereas in implicit we won't actually solve for the model distribution, but we will just sample from it. So we will learn some distribution, but not exactly. We will just learn the model that can sample from the given distribution, right? Things will be clear later on, but these are two distinct flavors, and of course this will be better because in implicit we don't have to explicitly compute or solve for it, because in real life scenarios it's not possible, right? Because it is one of the fundamental problem, as I said, in density estimation in unsupervised learning. So of course this will be better, and we will see what GANs are. I'm not like, it might be alien terms right now, so we will see in which category GANs will form, if you know GANs. If not, it's okay. So we will go from autoencoders, then variational autoencoders, and then we will go to GAN, and we'll motivate ourselves that what are the drawbacks of all the models so that we need GANs and so on. So, and we'll also see Python and so on along with PyTorch as well as TensorFlow. So everyone will be satisfied if you are a big fan of TensorFlow or PyTorch. So we will see both. Now, why generative models? So, for example, let's say we have a Tesla autopilot task you might be aware of. So in Tesla, in most of the training data will be in autonomous driving cars or roads or trees or buildings, right? So these are so let's say we have learned this distribution now. So we already know that the tails are the outliers, and in between is our actual data. So while having such a task at hand, that is Tesla autopilot task, we know that what can be the outliers. Let's say we are driving through an airport where our Tesla autopilot can see some plane landing, right? Then it might misbehave that, oh, this is, what is this? I don't know this because I don't have this image or this data while training, right? So the same goes for some sudden pedestrian crossing or some animal crossing suddenly, right? So these are the things which are outliers, and this is how generative model can tackle outliers in autopilot tasks. So here the summary is that simply detect the outliers in the distribution and you are good to go. And also using the outliers during the training will give us better results, because now the model knows that this is an aeroplane or this is some of the animal that is coming across, right? So this is how generative models are used. This is one of the use case. There are many others, like we can have image to image translation, we can generate new images like artistic paints and so on. So the list is endless, and I will make separate videos on all this stuff, so don't worry about that. This is just a motivation video, that very first lecture of generative modeling. So now there are, as I said, we will start with autoencoders, but here we will I have just listed variational autoencoders and GANs. And of course from this image you can conclude that GANs are more powerful than VAEs, but these two are called latent variable models. Why? So what is latent variable first? Let's discuss that, and then we will go to autoencoders. So what is a latent variable? So if you can see this, that this is an autoencoder architecture. So it's really simple, that there is some neural network architecture, CNN or whatever, and this is also a neural network architecture in decoder side. So what we do, let's say we have an input image X, and we just compress it to some lower dimension. So you can see here it's higher dimension image, here you can see just 3, so it's a lower dimensional image. So it is just a lower dimensional representation of some higher dimensional image, and that's what we call as latent variable Z. So what are those variables? So as you can see, these are the variables that are derived from some observed variable. This we can observe, but inside we don't know, because this is layer inside, right? It's a hidden layer. So latent variables cannot be observed. That's it. So how now, what is at autoencoder? So if you might think that we are just compressing our higher dimensional image to a lower dimensional image, and again we are decompressing it, and at the end we are getting the same image, and you can see it's not perfectly same, little bit blurred, and that's why we call it XCAP. So the end goal of the autoencoder architecture, because at the end it's a generative modeling, so we need to learn how to generate any image that is given as an input. But you might think like we are duplicating our efforts, right? That we already know the image, we already have the input image, why we are regenerating it? Just use whatever we have, right? Of course we will do the same, like we are duplicating our efforts, but it's not like that. We will train this model which can minimize, so this is our loss function, and which can this can be squared as well. So we will just take pixel difference and we will square it, and we'll try to minimize this loss until we get our minima. So, or we can say our model is trained, in other words. And after that, if we will give any input to this image, it will generate the output image, which is this 4, right? Because model has learned this, right? But how this can be useful? Like we are duplicating our efforts, right? So this is deterministic. Like every time I'll give any image, right, it will generate the same image. So this is a deterministic. So we need some probabilistic stuff or stochasticity in our output. And here comes into play the variational term. So this is just an autoencoder that it just encodes, then decodes, and try to train it. But what variational autoencoder will do, you can see here that let's say we have input image now here. This is just the image is changed, but the architecture is the same. So in AE, this is autoencoders, we just have our latent variable and the decoder and so on, right? So here you can see that encoder will learn Z given an X, whereas the decoder will be the other way around. That is, it will learn X given Z, the distribution. At the end, as I explained, like all this is a distribution, right? But now what happens in case of VAEs? So in VAEs, we add some stochasticity by this mean and variance. And you can see it's a Gaussian, and that's why it's called VAEs. So here I'll stop for this video, and we will continue from this point that how VAEs can help and how this stochasticity can help us to generate different images. So you will see here that uh, the images here at the output side is not same as the image at the input side. Why? Because there is some stochasticity involved, right? It's not like we will generate exact same thing. We will generate images of persons only, but little bit different. It will look, you can see like they are differing a lot, right? But they are all images of some person, right? So this is what a deep generative model is capable of, and we will start from variational autoencoders in our next lecture. Thank you.